Students, let us start the session today, guys. So in today's class, we are going to discuss about flip-flops. What are the basic flip-flops we have and their truth tables, okay, and how the basic block diagram of each flip-flop is looking like, and how the circuit diagram of each flip-flop is looking like, and how they are going to be operated. We are going to see clearly, guys. Okay, so that is our today's session. We are going to discuss about flip-flops clearly, guys. Flip-flops are actually, we are going to discuss about these four flip-flops: SR flip-flop, D flip-flop, T flip-flop, and JK flip-flop. Guys, before we discuss about flip-flops, we have already discussed what are latches actually. Okay, in latches also we have seen how SR latch look like and how D latch look like. Its truth table, okay, everything we have discussed already, guys. How the basic operation look like, and with applying of different kinds of inputs and different kinds of present state, what will be its output or next state, we have seen already in the last session. In today's session, we are going to discuss about flip-flops, guys. Okay, guys, remember in these flip-flops will be highly used in a design of multi-vibrators. Guys, you have seen so many multi-vibrators in pulse and digital circuits. Okay, starting from a bistable multivibrator, monostable multivibrator, astable multivibrator. In all these multivibrators, we are using flip-flops only to stay into the states. Okay, guys, do you remember in bistable multivibrator we will say two stable states? Okay, one will be 0 state and one will be 1 state, guys. Okay, so these flip-flops are used in multivibrators in order to design any multivibrators to move into different states, guys. Okay, different stable states. Here also we have two stable states. We can clearly say one is a 0 stable state, another one is 1 stable state, guys. Okay, these are the stable states we have, and that is a main application of flip-flops. These are used in design of multivibrators. Okay, let us go and see each flip-flop, how it's looking like and how it is going to be operated. Look at here, guys. First of all, we are going for SR flip-flop. You can see, guys, in SR latch also we have same kind of inputs. SR, S means set, R means reset, guys. SR are the two inputs we have in SR flip-flop. S is set and R is reset for a flip-flop we have. Okay, we are going to design this SR flip-flop here with the help of NAND gates. Similarly, we can design any flip-flop with the help of NOR also, NOR gate, because it is also a universal gate. Not only with the help of NAND gates, with the help of NOR gates also we can design any flip-flop. SR flip-flop, D flip-flop, T flip-flop, and JK flip-flop. We can design all the flip-flops with the help of all the universal gates. Also with the help of NAND gate, or else with the help of NOR gate. We can design with any flip-flop universal gate we have, guys. But in the today's session, we are going to see how the design can be done with the help of NAND gate here. Look at here, guys. This is the information regarding SR flip-flop. You can see this is the basic block diagram of a SR flip-flop. SR flip-flop. You can see a input S and another input R, and two outputs you will have, guys, Q and Q bar. Okay, that is a basic block diagram, guys. Okay, S is one input, R is another input, Q and Q bar are the two outputs we will have for SR flip-flop. Guys, I told you in flip-flops we will use clocks to excite any flip-flop. Okay, whereas how you have enable in the latches, we use a clock as a triggering element in order to change or shift your state in a flip-flops. So we have shown an extra element called C or CLK, clock in short form. We will be denoting in basic block diagram. Okay, so this is a basic block diagram, guys. Three inputs we can see. One is S, another one is R. Along with that, we will have a clock to trigger the given input. Okay, to trigger the flip-flop. And two outputs usually we will have for a flip-flop, that is Q and its inversion Q bar. Okay, that is the SR flip-flops basic block diagram, guys. Okay, along with that, I am showing you SR circuit diagram, SR flip-flops circuit diagram, guys. You can see the two inputs are given, S and R. This circuit diagram also, guys, same as like your SR latch, gated SR latch. In the place of enable here, I'm having clock in here. In the place of enable, I'm showing clock C here. Okay, The circuit diagram remains same. Okay, S is given as input, R is given as input here. To trigger, we have clock in here, and two outputs Q and Q bar can be seen in here, guys. Okay, Q and Q bar can be seen in here. When I'm giving the different inputs with the different present state, 0, 0, 0, 1, 1, 0, and 1, 1, with 0 as present state, with 1 as present state, will be denoting its next state, guys. Qn plus 1 we'll call it as basically next state, or output we call it as, will be determined with the help of truth table, guys. Remember, guys, in flip-flops, triggering is of two types. I have explained you already. Triggering is of two types. One is positive edge triggering. Second one is negative edge triggering. We can use anything, guys. Okay, we can use either positive edge triggering or we can use negative edge triggering. That is our wish to use anything. If you are selecting positive edge triggering, we will show the clock like this, or else we'll be having a bubble or inverter in the place of clock. Bubble or inverter will be placed extra in the place of clock. That shows you are using negative edge triggering in SR flip-flop, okay, which doesn't affect any operation, guys. You can select either positive edge triggering or negative edge triggering. That is our wish. Most of the cases we will use negative edge triggering only, which is more suitable for us. So we'll use negative edge triggering in most of the cases, which suits us to explain the operation. That's why I use mostly the negative edge triggering, guys. This triggering is nothing but a extra input or extra voltage that we can supply to the given circuit to shift its state. Okay, guys, I told you, if you are giving 0, 0 as my input, suppose you are getting an output 0, then you're giving another input 0, 1 as my input. Automatically, by giving the input another input, the output cannot be changed. The output cannot be changed here, guys, unless otherwise you apply a trigger to the given circuit. That trigger will make sure your state is going to be changed according to the given input and previous state. Guys, you be clear with this. In sequential circuits, if you want to change the state, okay, your output is depending on present state and also with your input. Okay, present state and input will definitely affect your next input, next output. Okay, next output or output. In that case, when you're designing a circuit like a flip-flop, if you change your present inputs, won't be enough to shift its state or to generate a new output. Along with the input and the present state, you should definitely give a clock as a trigger in order to change its states. Okay, to change its state. That trigger input will definitely will affect the circuit to change its state. That is what will be happening in flip-flop, guys. See here, I'm showing you the truth table of a SR flip-flop, guys. Okay, so you can see, guys, here in the clock I have kept an empty. You have to select whether you're going to give positive edge triggering or negative edge triggering in the circuit. Look at here, guys, I'm showing you in the white screen how you're going to denote whether you have selected a positive edge triggering or negative edge triggering. Guys, truth table consists of these contents. One is clock, okay, clock. Then you're going to give the two inputs, S and R, the two R are the two inputs you're going to have. Apart from that, you have the present state. Present state is denoted with Qn. Okay, this denoting of the elements will be different in different books or different areas. Don't get confused. Qn I'm denoting, or Q I'm denoting, writing here to denote my present state. To denote your output or next state, I'm denoting it with Q of n plus 1. Okay, Q of n plus 1, which is your next state, guys. And I'm going to write what state it is present now. Okay, what state, whether it is no change state or it is under set state or under reset state, or which is under any other state, to denote that I'm using here. Look at here, guys. If your circuit is in positive triggering, if you are using positive edge triggering to denote or to trigger the circuit, your block diagram should be like this. I have two inputs I have shown you, guys. One is S and R are the two inputs I have in a SR flip-flop. SR flip-flop consists of two inputs and two outputs. Q and Q bar, we already know that. Okay, Q and Q bar, you already know that, guys. Along with that, I have shown you a extra thing. CLK will denote in short, which is called clock. If you are using positive edge triggering, you should denote the clock like this. Or else, If you are using negative edge triggering, your denotion of the clock should be like this. Inside this, you should have a bubble which denotes you are using negative edge triggering. If you are using positive edge triggering, you denote like this. Okay. If you are using negative edge triggering, okay, inside that triangle shape, you should have a bubble which denotes inversion of positive is negative. Here we are going to use negative edge triggering to change your states. That is a symbol here, guys. This is about block diagram representation in here. You already know how to denote your circuit diagram for SR flip-flop, and operation we have already seen with the help of SR gated SR latch. Let me explain you how the states will be with the help of truth table. Guys, if you are using positive edge triggering, positive clock to trigger, your clock symbol should be shown like this in the truth table always. If you are using positive edge triggering to change its states, you should use this kind of symbol in the clock. Or else if you are using negative edge triggering of the clock will be denoted like this. Okay, that is our wish, to denote it as a positive edge triggering or negative edge triggering, which doesn't affect the operation at all or output at all. You can trigger your SR flip-flop either at positive edges or negative edges to change its state. That is our wish. But to denote for representation of clock, either you have to show a positive edge triggering or you can show negative edge triggering. You should show like this, guys. For example, if I'm taking positive edge triggering, clock should be shown like this. Now, guys, you have to say this to me. If I'm taking 0, 0 as my input, and if I'm selecting 0 as my present state, what will be your next state, guys? Generally for a SR flip-flop, if I'm using 0, 0 as my input and 0 as my present state, what will be your next state of a flip-flop? Generally, this will be 0 always, because when I'm giving 0, 0 as input, that state is called as no change state. No change means your present state. What is your present state? That as it is will come to your next state. Okay, no change state means, okay, what is your present state, that will as it is come to the next state. That is why it is called no change state. That is happening when I'm giving the inputs 0, 0. Let me go for the next condition, guys. I'm using positive edge triggering and I'm using 0, 0 as my input, and my present state I'm assuming that it is under 1. It is 1. Guys, tell me what will be your next state when I'm giving 0, 0. What will be your next state, guys?
1, sir.
1 always, because 0, 0 denotes no change state. What is your present state? That will be coming to your next state as it is. So the first input is over, guys. That is 0, 0 combination. Let us go for 0, 1. Next input condition. I'm denoting positive edge triggering, guys. I'm taking 0, 1 as my input. If I'm taking 0, 1 as input and if I'm taking 0 as my present state, guys, I explained you already in gated D latch, gated SR latch. If I have 0, 1 as my input combination, what state we will get?
Reset states.
Yeah, reset state. Okay, you will get reset state. In reset state, always your output is
0.
0. And I'm taking another condition, guys. 0, 1 input. Okay, 0, 1 input with 1 as your present state. Okay, I'm taking the next condition. I'm denoting positive edge triggering of the clock. This is mandatory, guys. Don't forget to denote clock. 0, 1 is my input. 1 is my present state. Automatically, your output is 0 since it is in reset state. Then let us go for the next condition, guys. So what will be the next combination of inputs? What would be the next combination of inputs, guys?
1, 0, sir.
1, 0.
Okay, 1, 0 with 0 as my present state. When I'm taking 1, 0 and 0 as my present state, what will be your next state, guys?
1, sir.
1. Why, guys?
Set state, sir.
Since 1, 0 is your set state. Okay, however, in the operation we have seen it will denote only your next state as 1. Again, I'm taking the next combination 1, 0 with 1 as my present state. What will be your output, guys?
1, sir.
1. Okay, 1, since it is in set state. For set state, always you will get 1 as your next state. Okay, then let us go for the last condition, guys. What it is?
1 1, sir.
Yeah, we have to take 1 1 as my S and R inputs. Okay, with the two different conditions we have for present state is 0 as one condition, 1 as another condition. Now guys, tell me, if I'm taking 1 1 as my input, okay, and if my 0 is the present state, what will be your next state, guys? What will be your next state? You'll get
Don't keep campus.
you'll get don't care condition, means you don't know what will be your output. Either you're going to get 0 or 1, you don't know. That is why we call it as a don't care condition. And this state is called as indeterminate state.
Determinant.
Indeterminate state. Okay, we don't know to determine what will be your next state. That is why it is called indeterminate state, guys. Okay, guys, are you all clear how to write how to explain about SR flip-flop now? First of all, we have seen how a basic block diagram look like for SR flip-flop. Then I have shown you what is a circuit diagram for SR flip-flop and its operation we have already seen with the help of gated SR latch. And this is the truth table of a SR flip-flop with the help of triggering of clock. Are you all clear with the SR flip-flop, guys? Any doubts in this concept? Any doubts in this concept, guys, in SR flip-flop? Guys, any doubts you can ask me now?
Sir.
No. Guys,
No,
can we
sir.
go for the second flip-flop we have?
Yes, sir.
Yes,
Yeah,
sir.
guys, let us go. That SR flip-flop is completely over, guys. Now let us go for the next one. Guys, the next flip-flop we got to see is D flip-flop. Okay, D flip-flop. Guys, D in the sense delay flip-flop, we can say generally delay flip-flop. Guys, I'm giving you very, very important point regarding D flip-flop. Listen and keep this in the mind. This D flip-flop is a not a separate flip-flop we have designed. D flip-flop is evolved from SR flip-flop alone. Okay, D flip-flop. By making small changes in the connections of SR flip-flop, we have designed this D flip-flop. Okay, by connecting the two inputs what we have in SR flip-flop, S and R, via a NOT gate, we are going to get the design of D flip-flop. Keep this in the mind, guys. D flip-flop is evolved from SR flip-flop only. By connecting the two input terminals of SR flip-flop, S and R, via a NOT gate or inverter, we are going to design D flip-flop. Why it is called delay flip-flop? Listen to this case, guys. Whatever the input you are giving for D flip-flop, whatever the input you are giving as input to the D flip-flop. Guys, remember, a D flip-flop will have only single input D and two outputs Q and Q bar. Okay, D flip-flop will have a single input D and two outputs Q and Q bar. So that either I can give 0 as my input or else I can give 1 as my input to the D flip-flop. Okay, either 0 or 1. Based on that input only, the D flip-flop has to generate its output either as a 0 or 1. The reason behind why it is called D flip-flop, D flip-flop as delay flip-flop is whatever the input you are giving to the D flip-flop, that will be shown as your output. For example, if I'm giving D equal to 0 as my input, your output also will be 0 in D flip-flop. If you are giving D equal to 1 as input to the D flip-flop, that same 1 will be shown as output in the D flip-flop. So whatever the input you are giving, that is delayed after some time and given as output, that is why it is called delay flip-flop. Let us see how it is happening, guys. See the circuit diagram, guys. Initially we are having S as input, R as input. This entire structure is same as your SR flip-flop, but only the change is that S input and R input are connected, S and R are connected via a NOT gate, You can see here, guys, this is your SR flip-flop. Now if you connect S and R via a NOT gate, inverter gate, you can design D flip-flop. A small change, that's it. We are going to connect S and R via a NOT gate. You can design D flip-flop. These two are connected to a single input line D. However, clock is mandatory. Let's look at the basic block diagram we have for D flip-flop. A single input D, clock is mandatory, guys, and Q and Q bar are your outputs. You can see this clearly. Now, let us go and see the truth table of D flip-flop, guys. Guys, you have to say this to me. Since I have a single input in here, I can give either D equal to 0 or else I can give D equal to 1 here, guys. Okay, D equal to 0 or D equal to 1. Tell me, guys, you have to say this to me. If I have D equal to 0 here, what will be reaching your S input here? If I'm giving D equal to 0,
0, sir.
what will be reaching your S? 0. If I give D equal to 0, that 0 will be passed through the NOT gate and what will reach your R here?
1, sir.
1. So you're giving 0 at S, 1 at R. 0, 1 in SR flip-flop is 0, 1 in SR flip-flop is what it gives you, guys. What output it will generate? 0, 1 means what state it is?
0, sir.
0,
0,
1 means
sir.
0, 1 means what state it is actually?
Reset state.
Reset state, sir.
Reset.
Or, yeah, in reset state, always your output is 0. So when I'm giving D equal to 0, your output is also 0. Clear with that. Now I'm going for the second condition, guys. If I give D equal to 1 in here, if I give D equal to 1 in here, your S is 1 and R is 0. Your S is 1 and R is 0. Guys, tell me, if I give S is equal to 1 and R equal to 0, what way this SR flip-flop will work, guys? When I'm giving S is equal to 1 and R equal to 0, what
Set
condition will
state,
move to? Set state.
State, sir.
In set state,
Output is 1.
in set state, what will be your output, guys? It is always 1.
1.
It is always
1, sir.
So, when I'm giving D equal to 1, your output is also 1. So that is why it is called delay flip-flop. What input is you are giving? The same will be given as your output. That is why it is called delay flip-flop, guys. See the truth table. When I'm giving D equal to 0, whatever may be your present state, either your present state may be 0 or 1, doesn't matter. Present state is not at all a case in here. What if your input is D equal to 0, your output is 0, and I can say it is under no change state or else it is under reset state. Okay, no problem. If I'm giving D equal to 1, whatever may be your present state, whatever may be your present state. Okay, if it is 0, no problem. If it is 1, no problem. It will automatically move into set state. Okay, your output will be always in set state. Okay, guys, do you understand delay flip-flop? What is the basic block diagram? How the circuit is going to work? And what is the truth table? Guys, in the clock, I have left alone. So either you can show positive edge trigger waveform arrow or negative edge trigger waveform. You should show definitely one thing out of it. Okay, guys, any doubts in this truth table of D flip-flop and in the operation of D flip-flop? Any doubts, guys? You have to say. Then if you ask, I will explain that. Okay, if there are no doubts, I will move for the next flip-flop. Can I move? Can I move, guys?
Yes, sir.
Can I move to the next flip-flop? Yeah. Then let us
Yes.
go to the next one, guys.
sir.
Let us move to the next one. Guys, this is one of the very, very, very important flip-flop. Why? Because we call NAND gate and NOR gate as universal gates. Why, guys? Why we call NAND gate and NOR gate as universal gates? Why do we call NAND gate and NOR
Without
gate?
using any gate, sir.
Yeah, without
Without
using
using
any,
any gate, we can draw circuits, sir.
yeah, without using any other gate other than NAND and NOR, we can design entire circuit. Only with the help of NAND or only with the help of NOR, we can design any circuit. That's why we call NAND and NOR as universal gates. Okay. Likewise, this JK flip-flop is very, very important gate. We will use this JK flip-flop in most of the cases in any design of multi-vibrator, something like that. This JK flip-flop is used in most of the cases. Okay, like this can be used, this can be called like universal flip-flop. JK flip-flop sometimes can be called as universal flip-flop. Okay, because it matches all the conditions most of the cases. Okay, guys, here also this JK flip-flop will have most of the cases same as like your SR flip-flop. Okay, First three cases. Guys, tell me in SR flip-flop, if I give 0, 0, what is your state? If I give 0, 0, what is your state in SR flip-flop?
No change.
No
state.
change,
Yeah.
sir.
In JK also same. No
Change.
change state. If I give J equal to 0 and K equal to 0, it is no change state. Guys, tell me in SR flip-flop, if I give S is equal to 0 and R equal to 1, what state we call?
Reset state, sir.
Reset state.
Reset.
Here in JK flip-flop also, if I give J equal to 0 and K equal to 1, it is called reset state. Guys, tell me in SR flip-flop, if I give S is equal to 1 and R equal to 0, what state we call it as?
Set
Set
state.
state. Here also in JK flip-flop, if I give J equal to 1 and K equal to 0, we call that state as set state. Okay. In first three cases, SR flip-flop and JK flip-flop will work in the same kind of way. Okay. For when I'm giving J equal to 0, K equal to 0, this JK flip-flop will move to same no change state. If I give J equal to 0 and K equal to 1, that JK flip-flop will move to set state. If I give J equal to 1 and K equal to 0, that will move into set state. Okay. First three conditions of JK flip-flop will be as it is like your SR flip-flop. Only the change you can observe in JK flip-flop from your SR is the last condition, that when I'm giving J equal to 1 and K equal to 1, the output state of your JK flip-flop will be different. Whereas in SR flip-flop, if I'm giving S is equal to 1 and R equal to 1, that state is called indeterminate state, which means that we don't know what output you're going to generate in SR flip-flop when I'm giving S is equal to 1 and R equal to 1. That is a major limitation we have. That is a major limitation we have in SR flip-flop. Guys, now you tell me what is a major limitation you have in SR flip-flop? First three states is okay. We are determining clearly. It is a set state, it is under reset state, or it is in under no change state. But when you move to the last state, when I'm giving S is equal to 1 and R equal to 1, that SR flip-flop cannot determine what state it is moving to or what output it can generate definitely. So we are going for it as indeterminate state. So in order to overcome that limitation of the condition when I'm giving S is equal to 1 and R equal to 1, I have migrated to JK flip-flop and I have designed in little different way your JK flip-flop apart from SR flip-flop here, guys. Okay, by taking feedback from the output of your flip-flop, we are going to design your JK flip-flop. This JK flip-flop also will have most of the circuit as your SR flip-flop. Apart from that, we are going to take feedback from the outputs and we are going to use that in the circuit to define the condition J equal to 1 and K equal to 1 to move away from indeterminate state, guys. Okay, guys, be clear. First three cases, J equal to 0, K equal to 0 is your no change state. J equal to 0, K equal to 1 is your reset state. J equal to 1 and K equal to 0 is set state. These three are same as like your SR flip-flop. Only the change you can find in JK flip-flop is when I'm giving J equal to 1, K equal to 1. And I will explain you what changes you can observe when I'm giving J equal to 1 and K equal to 1 with the help of circuit we have here, guys. Look at here, guys. This is the basic block diagram of your JK flip-flop. J is one input and K is one input, and you can see the clock connection in here, clock connection, and two outputs you have are Q and Q bar, as it is, guys. Okay, and this is a circuit diagram. Okay, logical circuit diagram you have for JK flip-flop. Guys, look at here what changes you can observe here. Look at here, feedback is taken from Q bar output to the J input, and feedback is taken from Q input to the another NAND gate in here. That is a change you can observe here, guys. Okay, so feedback connections are taken into the input, Q bar to the J and Q to the K. We have taken feedback. That feedback will eliminate that indeterminate state. Okay, this indeterminate state can be eliminated by taking feedback connections. Guys, this kind of connection you cannot see in SR flip-flop or D flip-flop. This only can be seen from JK flip-flop. That feedback connection is extra element we are getting in JK flip-flop. From Q, I am taking a connection. Okay. From Q bar, I am taking one connection to this part and Q to this part. You can see that is the only change you can see. We are using 3 inputs in here, guys. Clock is mandatory. However, we are taking clock. Guys, can you see the difference from SR flip-flop to JK flip-flop? What are the connection changes in the connections? Where the connections are changing from SR to JK? Can you observe? Guys, tell me where the connections are changing in JK to SR. Tell me where the connections are deferred from SR to JK. What connections are different here, guys? Yeah, these
Q bar,
feedbacks
sir.
are new. These feedbacks are new. In SR, we have only 2 input lines, guys. I will show you once again. See, S is 1 input, R is 1 input, and interconnection between these 2 is common with a clock. But in JK, a connection is taken from Q bar clock feedback and given to the NAND gate. And from Q, I am taking another input line I'm giving in here. That is the difference. Okay. From Q bar, I will take a feedback line and I will give here. And from Q, I will take a feedback line, I will give here. And my inputs are J and K here. Guys, in SR, it is set and reset. In JK, it is nothing like that. J and K is the short forms of the scientist who invented JK flip-flop. Jock Kilby something. I don't remember exactly the name of the scientist. On his name, they have named the inputs as JK, Jock Kilby, I think so. J and K are the names of the short names of the scientist who invented JK flip-flop. That is why they call the 2 inputs as J and K. So that by taking the feedback, we are designing this JK flip-flop. Guys, look at here. I'm designing the, I have shown you the truth table of JK flip-flop. First 2 conditions. When I'm taking 0, 0 as inputs, with my present state is 0 and 1, I'm going to the no change state. If it is 0, out next state is 0. If present state is 1, next state is 1. When the inputs are 0, 0. Next input is 0, 1, guys. You already know when I'm giving 0, 1, it will move into reset state. Whatever may be the present state, okay, whatever may be the present state, next state will be 0. Third condition, if I'm taking 1, 0 as my input, however, you will move into the set state. In set state, your outputs will be 1, whatever may be the input present state. Guys, look at this is peculiar and new in JK flip-flop, this condition. When I'm giving 1, 1 as my input in SR flip-flop, what state you have reached in SR flip-flop, guys? When I'm giving 1, 1 as my input, what state you have moved in SR flip-flop? Indeterminate state, guys. But here you will move into toggle state. Toggle, okay, toggle state, guys. Toggle state means if your present state is 0, you will move to the state 1. If your present state is 1, you will move to next state 0, opposite to your present state. Oh, okay. If your present state is 0, next state will be 1. If present state is 1, the next state will be 0. This state is called toggle state. Okay, what is meant by toggle state, guys? It is exactly the inversion of your present state. Toggling means exactly the inversion of present state. If present state is 1, 0, next state will be 1. If present state is 1, next state is 0, guys. You can easily determine what will be the output or next state using JK flip-flop. Whereas in SR flip-flop, I cannot determine what state that you're going to move. Okay, you're moving to. Okay, so using JK flip-flops feedback connections, we have moved into toggle connection, toggle state when I'm giving J equal to 1 and K equal to 1. Okay, with the help of present state, what I have. Guys, do you observe the difference between SR flip-flop to JK flip-flop?
Yes, sir.
Yeah, where you are observing the difference? Where you are observing the difference, guys? Where you are observing the difference? At which input you are observing the difference from SR to JK flip-flop?
So feedback connections are from J to and Q bar and
Yeah,
K
when I'm
to
giving
K, sir.
J equal to 1 and K equal to 1 input, I can clearly observe the difference from SR flip-flop to JK flip-flop. Okay. So in SR, when I'm giving S is equal to 1 and R equal to 1, I'm moving into indeterminate state. Whereas in JK flip-flop, when I'm giving J equal to 1 and K equal to 1, I'm moving to the toggle state. What is happening in toggle state, guys? What is happening in the toggle state? Tell me. What is happening in the
Inversion
toggle
of
state?
the present input, sir.
Inversion of present
Yeah, in toggle state, if your present state is 0, you will move into one state or set state. If your present state is 1, you will move into reset state 0, guys. Okay, that is how you can see the toggle state. So by taking this JK flip-flop as your basic flip-flop, basic circuit connection, we are moving into the next flip-flop, that is T flip-flop, guys. T flip-flop. You have seen how we have designed D flip-flop with the help of SR flip-flop. You can see, guys, how we have designed SR to D. What connections we have made here to design D flip-flop from SR? What connections we made to design D flip-flop from SR? What changes we made, guys, from SR to D? By making what connections we have
Non-inverter,
converted?
sir.
What?
not can get initiation, sir.
Both the inputs S and R are connected via a NOT gate. So by making that
NOT gate,
small
sir.
change, okay, connected S and R inputs via NOT gate. That is what we have made change from SR to D. To design D flip-flop, we have connected S input and R input via a NOT gate. In the same way, to design your T flip-flop, toggle flip-flop, guys. T flip-flop means toggle flip-flop. To design this toggle flip-flop, we made a small change in JK flip-flop. Guys, observe this JK flip-flop connection, circuit connections. Observe the circuit connections of JK flip-flop. To design the toggle flip-flop or T flip-flop, we are going to make a small changes in JK flip-flop. Look at here. You can see JK flip-flop, how it is looking like. Now, let us go to the T flip-flop.